off.
Hello, my name is Obi Anamnachi. Today I will be giving a webinar on data preprocessing, Spark and Cassandra for machine learning. This is actually a part 2 of a series. The first part is not a webinar, but a blog that is hosted on Anant's blog at blog.anant.us. And it's about how to set up the environment that you're going to see later today in the demo. The way this is going to work is it's going to be split up vaguely into about 3 parts. We're going to have a sort of introduction section where we talk about data preprocessing, what it is and why we need to do it. We're going to take a look at some specific types of data preprocessing. This is separate from how they would be specifically done in this environment with Cassandra and Spark. And then we're going to have a demo showcasing some of these and how they work in an environment built up with Cassandra and Spark. So if you have seen the blog post that is the part 1 of this series, you'll know we are, you will recognize this image first of all, and know that we are over on the left, the very left of the section called Preparation, where raw data is being transformed into data with features and labels. And basically the way that that happens is data preprocessing. Generally, it's a set of transformations that you apply to your data that prepares it for use with machine learning algorithms later on. Different machine learning algorithms want data formatted in different ways, but when your data comes in the first place, you don't really know what it's going to look like or if it'll be in a format that is relevant to that algorithm. So your fields might come in various types. You might have values missing from your data, and you may have fields which are just copies of each other, and all those things can cause problems depending on what type of algorithm you want to work with. Data preprocessing is also important aside from the fact that it allows us to use machine learning algorithms at all, in that the process of it gives us some insight into our data. So we can start gaining value, gaining new insights from our data before we actually put it into learning algorithms. So the types of preprocessing that we're going to talk a little bit about today are vectorization, imputation, standardization, encoding, and PCA. And there's an image over here on the right that talks about some of the different subfields of data processing. And we'll be getting a little bit into several of these. Though most pre-processing methods fall into 1 or possibly 2, some even more so than others. So starting off, we have vectorization, which is less mathematically complicated than anything else we're going to talk about today. Vectorization is important because machine learning algorithms work on a mathematical basis, generally with linear algebra. So you need linear algebra vectors or matrices to feed into them. So vectorization is that process of taking your data, which can be, say, in databases in different tables, or potentially in a single database, but in columns that are not quite conducive to feeding into a machine learning algorithm, and you combine them into a single vector, which is suitable for being fed into your machine learning algorithm. So this image on the right here is a little bit about, it's more like something you might see if you're preparing to work with a neural network. Basically, your data is over in the X field. Each one comes in a vector. So X0 is a vector of some length, X1 is a vector of some length, and all of those are being multiplied by weights, which is generally how a neural network calculates its output. So in this specific environment that we're going to be working with later today, Spark has a specific class called Vector Assembler, which takes your columns out of the data type that Spark most wants your data to be in and puts it into a format that your algorithm most wants it to be in. By the way, I forgot to mention this earlier, but if you have questions, put them in the chat and I will try to get to them either before we get to the demo or during the questions section after the demo. Our next method of pre-processing for today is imputation. It deals specifically with missing data. And of course, the easiest way you can deal with missing data, this is within your data set, is to drop any rows that have missing fields. But you don't always want to do that, especially if you have a lot of those fields, well, a lot of those rows, because you feeding less data into your algorithm generally makes it less accurate. And generally the method that we use to do imputation is mean imputation, where you look at the column that the missing piece of your data goes into, and you calculate a value for that missing piece based on the ones that do exist for that column. But you don't necessarily have to use the mean. You can use the median, lowest, highest values for that column, or a random value from a different example from that column. You can also use a predictive model. I've called it machine learning imputation here because I don't know if there's a specific technical term. But if you train a predictive model to work using your existing data, you can then feed in your data with the missing field and the model will predict a value for that missing field. This is a little bit more difficult to do if multiple fields are missing for the same piece of data, because you'd have to do things like decide whether or not some of your existing data with different fields missing should be fed in and what should be taken into account when calculating these. Something we're going to talk about a little bit in the demo later that's relevant to imputation is that your missing fields won't always look the same. So this is important because generally when you talk about imputation, you're talking about null fields, which are all marked as null. There's no value in them at all. Whereas depending on how your data was put down on paper into a database, whatever, there might actually be a value there, but it's out of range. Maybe your range for a certain field is positive integers, but there's a -1 or something like that. That could mean that data that your algorithm would technically take, like if you fed the value in, would still give wrong results. So next we're talking about standardization, which is about centering your data around a specific value, usually 0, and scaling it to within a certain range. So you can see in the image over on the left, our first distribution has a center point of mu, which is an unknown value, and an RMS of sigma. And on the right, we have that this data standardized so that it's centered around 0 and mean value of 1. This is important because a lot of algorithms, well, some algorithms need your data to be centered around 0, and some will only work with positive values, and some work best when you have data between 0 and 1, et cetera, et cetera. There are all sorts of reasons to standardize your data. Depending on exactly what you want to preserve about that data, it can be a good or a bad idea. Next, we're going to talk about encoding. So generally, encoding is the process of turning values into other values. The ways that this works is you can do binary encoding, which turns values that don't have any fields in your data that have only 2 possible values can be turned into integers with the value of 0 or 1, or Boolean values if your algorithm will take them, like say a binary tree will work with Boolean data, but a neural net needs its categorical values in integer form. Categorical encoding is similar. It works for fields with greater numbers of possible values as long as that number is still finite. So you would label these fields in between 0 and whatever number you want, depending on how many possible values they are, and each possible value has to become a unique integer. This works well for string fields in your data as long as they're not completely free form. As long as they're categorical, you can use categorical encoding for them. And then one-hot encoding is a similar type of encoding to categorical, but each possible value just becomes a place in a string of binary digits. So if you have two potential outcomes or three potential outcomes, you might have 1, 0, 0, 0, 1, 0, and 0, 0, 1 as your three possible values for that field. Some algorithms prefer one-hot encoded values or prefer to produce one-hot encoded values rather than normal categorized integers. And then the last method of data pre-processing that we're going to talk about today is also the most complicated mathematically. Principal component analysis is data processing that cuts down on the number of fields being fed into a machine learning algorithm, as well as it telling us which of those fields are the most important for explaining variance in our data. So you can see in the image on the right, we have our data graphed along normal axes. It sort of bunches up in a diagonal line. But with PCA, we shift and we rotate where our axes are so that there's more difference between the values as they're shown and fed into our machine learning algorithm later. If we wanted to, we could use PCA to turn this two-dimensional data set into a one-dimensional data set. We, of course, do lose some of our explanatory power that way. But if we had a data set with, say, a million possible, like a million dimensions, we might very much want to cut down that number to a more reasonable number that could be fed into our machine learning algorithms. And generally the dimensions chosen for your PCA are the ones that explain the most variance in your data. So you can see in the picture on the right, the PCA first dimension explains a large amount of the variance of the data, even compared to our original x-axis in that picture. And then our y-axis and any other axes are made to be orthogonal to that, so that you don't lose your normal like spatial reasoning ability. Your data is just transformed to fit. So moving on to our demo. Again, this is an environment set up with Cassandra and Spark. And we'll be working in a Jupyter notebook, which will be made available by the time that the video for this goes up on YouTube, or the blog post relating to this goes up on Anant's blog. So you should be able to find links to both of them there when those go up. So we're starting generally just by importing all of the needed modules. We'll be using Python and PySpark for this. And the first thing we want to do is we want to make some of our helper functions available. So the first one is one for having good formatting with Spark data frames. They're easily readable this way, and it really helps you make sense of your data. And the second is one for calculating correlation matrix, which is a necessary step for primary component analysis, which we will be doing as part of this demo. And then we're moving on to where we create our Cassandra environment. Starting with our key space and tables. And the first data set that we're going to be working with is the classic iris data set, which I think was one of the original like Stanford machine learning data sets. And we want to load it into our Cassandra table. So currently this data set is stored in a CSV file. in the environment that this demo is taking place in. And we want to load it into our Cassandra table and start our Spark session. So the first thing we're doing here, once we've started the Spark session, is we are feeding that Cassandra table into it. So we now have a Spark data frame called irisdf that contains all of the data that was in this CSV file and then in the Cassandra table. So there are 150 rows in this data set, and we can see what those look like by using the helper function that we got earlier. So you can see there is an ID field. There are 4 numeric fields and a string field. The first thing that we're going to do is encoding. So we are taking the species column, which is the output that we want our machine learning model to generate in this case. And we are going to transform the column in the data frame, species, into a column called label, which is integer encoded. So you can see there is now a field called label, has values of 1, 0, or 2, depending on the species that was originally there. So the next thing that we're going to do is we are going to plot this really quickly. We can see our data set has 50 examples of each target class. And this is in preparation for primary component analysis. Okay. So this is our plot of our relational data according to various axes. So all of these middle ones plot a particular field against itself, but these other ones plot fields against each other. So you can see this plot here plots sepal width in centimeters versus the label that we show. And all of the label fields are, of course, very well separated because they're just encoded. There are only 3 possible values for them. And so, of course, the data is very well separated in the y-axis, but it's less so if you imagine all these stacked on top of each other in the x-axis. So generally, you'd have to use a combination of traits, unless you find something maybe like this up here, which is, well, no, that's the ID, which is a generated field rather than one that has value to the algorithm itself. But essentially, if you can find fields that are well separated, then your machine learning algorithm will probably do very well on the data, depending on what algorithm you're using. But there are some algorithms that will fail if presented with data that isn't linearly separable. So it's a good thing to keep an eye on. Next, we want to plot our correlation matrix so that we can tell which values specifically are highly correlated with each other or highly correlated with the label that we want to predict. And one of the things that you want to keep an eye out for here is fields that are different on paper but have very high correlations. Because in that case, they may be redundant, especially if you see a correlation of 1 that isn't along this diagonal here. This may be a redundant field that you might want to get rid of, depending on how it interacts with your other data. Next, we are going to do some vectorization. Because we have the 4 fields, petal length in centimeters, sepal width in centimeters, petal length and width in centimeters, and sepal width and length in centimeters. But they are all in separate rows on this table, which would make it a bit difficult to feed them into a machine learning algorithm without further processing. So we do that processing here. We take our vector assembler class, and then we combine everything. We combine all of those 4 columns into a single column with a list with 4 values in it that's called features. And that features column is what we'll be feeding into our algorithm later. Next thing we want to do is split our data into train and test splits. This isn't something that we're really going to talk about in great detail here, but will probably be the topic for the next webinar in this series, which will be about train test splits and validation methods. So you can see our training data set has 120 of the original 150 values, and our test data set has the last 30, making the 150 total that we saw earlier. This is selected randomly, so hopefully you will be able to train on your data and not like have one of the labels completely left out of your training set. Next, we start our PCA. So we've taken our 4 field values and created a 4 field PCA. This does not, it would not help in the situation I described earlier, where you take your million feature data set and turn it into a million value PCA. That might help a little bit in that your axes might be better aligned to tell the difference between what those values mean for your algorithm. But they would not be helpful in decreasing the amount of time that it takes to process that data. So in this case, we move on to plotting the explained variance of each of the generated axes. You can see that the first axis explains about 90-something% of the variance in our data, whereas further removed axes from that explain less and less. In this case, we look at this and we say, we probably don't need these ones over here. So we train our model again. Well, we're creating a new model and then training it on the training data again. This time with only 2 features in its PCA output. So you can see here that these are actually the same 2 values from up there, but our model transforms them into only those 2 instead of having 4. So to test it, in this case, we're going to use a random forest classifier. The hypothesis here is generally that PCA won't have an extreme deleterious effect on the accuracy of your algorithm. So if you see a graph like this where your first 2 or however many features are explaining the vast majority of variance, when you feed the transformed features into your machine learning algorithm, they shouldn't have a huge bad effect on your algorithm's performance. So, and this is generally how machine learning is done in Spark. You create a class for your classifier, you train it on your data, and you can then predict by feeding in your test data, and it will generate a row called predictions, or a column called predictions. And you can see all the ones here. It got all of them right. The original label was 1. The calculated label was 1. The original label was 2. The calculated label was 2. And then calculating our accuracy over the entire test set. This is a 96% accurate model on the 30 test examples that were generated. And then we can also test using the PCA the post-transformed features and get our predictions out. In this case, you can still see these ones were all predicted correctly, but when you go look at the accuracy, it has decreased a little bit. So the primary thing you're wanting to get out of PCA is if feeding your data into your algorithm to train it is taking a ridiculously long time, and you think that you could get better performance by reducing the number of fields being fed in, that's when you might want to use PCA. Whereas if you care a whole lot about the accuracy of your model on the test set and are not worried about overfitting, which may be a topic for a future webinar, you might want to not use PCA and stick to your original axes. Okay, so we're moving on now to the second portion of our demo, where we work with some of the other methods of pre-processing that we have not seen above. And in this case, we'll be working with a data set on the prevalence of diabetes in the Native American population. So once we have loaded into our Cassandra cluster and then pulled that into a Spark data frame, we have 768 values, and to get a good idea of them, you can see here. So we have a lot of fields, and the primary part of what we want to look at here, like the primary method of data pre-processing that we're looking at here is imputation. But as you can see, none of these values say null or none or missing or nan or anything like that. In this case, there is missing data, but it's all been written down as 0, which means we have to be a bit careful. So the first thing we want to do is count how many zeros are in each field. So for each field, we print out the name and then the count for zeros in that field. So you can see blood pressure has 35 zeros, BMI has 11 zeros, label, which is diabetes or no diabetes, has 500 zeros, plasma glucose has 5, serum insulin has 374, times pregnant has 11, and tricep thickness, which is, it's a measure of like the thickness of the skin on your tricep, which somehow helps determine if you have diabetes, has 227 zeros in that column. And as you can tell, some of these values 0 is out of range for, and others it is not. For example, the label field is perfectly fine to be 0 because in that case, it just means they do not have diabetes. And times pregnant is also very clearly allowed to be 0. It just means that they have not ever been pregnant. But some of these other fields definitely should not be 0. Blood pressure probably should not be 0. BMI also probably should not be 0. So we go into these categories individually, and we replace all of these zeros with null values specifically. A link to the notebook that is not available yet. I have the file, but it is not up online yet. I can probably put it in Google Drive at the end of this presentation, and I can share the link in the chat then. But we're just about done, and I can make it available pretty soon after that. So moving on, we do another count of how many zeros are in each column, and some of them should have changed and some of them definitely should not have changed. So we left the label field and times pregnant field as they are. And then you can see here that in each case, we've replaced the 0, which is out of range for the field, with not a number. And this allows Spark's imputer class to go in and replace all of those missing values with numbers. So I added this example specifically because there was no imputation necessary in the one we used above. All the values were there and within the ranges that they should have been. But we did talk about imputation in the presentation earlier, so I felt like I should provide an example. But that is the end of our presentation for now. This has been webinar with Anant Corporation. My name is Obioma Anamnachi. Contact us if you would like to speak more about these topics or would like to work with us. Any questions?
Hey, can you hear me?
Yes.
Hey, thanks for the presentation, Obi. Just a kind of, using Jupyter Notebook, it almost, feels like, you're just doing a standard notebook and you're just dealing with CSV data, but obviously you're using Spark and Python. How much work did it take for you to take what you know from Python, basic machine learning that everybody kind of plays around with Jupyter Notebooks, and then apply to what you're doing with Spark? And then how much more work did you have to do around the data, the Cassandra layer as well?
Okay, sure. So I will say it's a little bit difficult to get your head around the syntax of working with Spark. That's one of the things I had trouble with coming up in the lead up to giving this webinar. But once you know how something is done in Spark, it's pretty easy to, and even once you've got a sort of feel of like Spark documentation and all that sort of stuff, it's pretty easy to find a way to do something that you would have done in your normal R or Python machine learning tasks and apply it into this Spark environment. And I know that generally we aren't really getting the value out of Spark here, seeing as this is a single computer, a single cluster. But it's easy to see how you would get benefits out of running this in a distributed way, like where the limitations of your single computer Python like environment are, and how Spark enables you to surpass them. And the other part of the question was about, the Cassandra and how difficult it is to like interact with your data in Cassandra for these machine learning tasks. But I wouldn't say that that added a lot of difficulty actually. If you have any experience with loading data into Cassandra, it is pretty easy once in an environment with Spark to pull that data out of Cassandra and put it into a Spark data frame, which you can then work with as normal as shown in this presentation.
Gotcha. One other question. So, with GPUs and obviously, like at least with TensorFlow, PyTorch, the ability to vectorize and do parallel processing on tons and tons of data points. Um, is that, would you say, is that mutually exclusive from what you're gaining in Spark, or is that you think it can work together? I mean, I'm aware of what these two things do, but I'm just curious as to what you think about that.
Can you ask again? I think I missed some of the detail in the beginning.
Oh, I'm sorry. I was saying, how would you compare Spark parallel processing to GPU parallel processing using, PyTorch and TensorFlow?
I see. So, I mean, obviously the point of both is to get you good performance when training your models and deploying them. And I think that, like, while I don't know if there's a setup for an individual to do something like that, I know that people like NVIDIA or like people with a large amount of both like server space and then a large amount of powerful GPUs can rent out that processing power. So I think they're not necessarily mutually exclusive. You could use the power of a GPU as a part, potentially as a part of this cluster to help you get faster processing, even if your data is distributed. But I don't know if current server architecture is set up for that sort of thing.
Gotcha. Very cool.
One second. Okay, any more questions? All right, I guess we'll finish up then. Thank you for coming to my webinar. Again, if you are interested in working with us or would like to discuss any of these topics further, you can contact us. At any of these email addresses or our website or phone number. Thank you for coming.